All right. Good morning, everyone. Friday. All right, GEO 319 lecture. Let's see. I can't hear you guys. Can you hear me?
I can hear you.
All right, I'm hearing you now.
Hi, sir.
Okay. So today I wanted to do some lecturing on sources of transport and thinking about our example of eutrophy. And we read Carpenter 2008, and it talked about eutrophy and eutrophication and nutrient cycles. So today I wanted to step back and actually think about how we get these sources of, or how do we get nutrients into the stream or water body to cause eutrophication. And this brings up a sort of broader topic of transport and transport mechanisms, which we've been playing with and talking about, but today I wanted to formalize in some lecture. So I'm going to share my screen here.
So when you talk about this, are you talking like leaching? And stuff like
Yeah, well,
those kind of processes?
we're going to talk about leaching. We're going to talk about ways which that nitrogen and phosphorus and all that good stuff that we don't want in our streams actually gets there. Okay, so let me erase this stuff. We'll come back to this equation, but for now we don't need it. All right, so I'm gonna draw a land surface here. Sort of gently sloping down to our stream. And we're going to think about, first of all, our critical zone. All right, so the critical zone was, let's say this is farmland here, so we got a bunch of crops. And up here, we're in the uplands, so we got trees. My trees have devolved today. Okay. So we define the critical zone as that zone between the tops of the vegetation and the atmosphere down to the bottom of our circulating water. All right, so let's say it's some depth down here, some imaginary depth. We have this unweathered, impermeable bedrock. Doesn't exist until you get really, really deep, but for now we're going to keep it. And this is some zone where active circulation or groundwater circulation is really low.
All right. Sir, so the critical zone goes all the way down to this bedrock or down to the water table? Or is the water table where it all occurs?
Critical zone extends from the top of the veg,
okay,
to the bottom of active circulation.
Right. So the granite, impermeable granite would be the bottom. Okay.
Now, I'd say my research and an active area of research right now is really considering this question. What is the bottom of the critical zone, and what is the bottom of this active zone of circulation? But for now, we're going to say there's some area where the groundwater circulation at least becomes slow enough that it's not that important for these biogeochemical cycles that we're talking about. I'm not exactly sure where that is, but that's the definition right now. Okay. So in Carpenter 2008, they talked about nutrients and what and the transport of nutrients into water bodies. When that happens, we get a big area of high primary productivity, so big algal bloom, all right? And then as that algae dies, it gets consumed and all the oxygen in the water gets used up, all right? So today what we want to focus on is the ways we actually get the nutrients in to the stream. And let's talk about both phosphorus and nitrogen. And let's think about phosphorus to start. So what were some of the ways through our readings so far? What are some of the ways that we have discussed, or that the papers have discussed, that phosphorus can get transported into our water body to cause eutrophication?
The paper made it clear that phosphorus was a solid transport. So where nitrogen was via either atmospheric or liquid, it was soluble in water. So the phosphorus, I think they said, was like mostly dirt, soils, rocks, breaking down of those things.
Okay, so one of the things that we might think of is the phases of transport, right? So how about phases involved in transport? And okay, so we could have solid. All right, so that's like mineral, soil, rock.
Mineral deposition, soil.
All right, and then we've got aqueous. All right, so that's dissolved in water. All right, and then we've got gaseous. All right, so transport, or well, we'll just say gas phase. So atmosphere, soil gas. Any other subsurface gas phase. Okay, so each one of these phases is going to has different transport mechanisms. So each one of these phases gets a different transport mechanism. So this controls. So as an example, how do you get how do you transport, say, solid phosphorus? How do you get that phosphorus into the stream? All right, it's in soil. It's Carpenter 2008 told us that it likes to stay in the solid phase. How does it physically get into the water body then?
Could it be dissolved by water or blown by wind?
Well, we just said it likes to stay in the mineral phase, so it's not, if it gets dissolved in water, it becomes aqueous.
What
So,
if water, instead of it dissolving, it and becoming solution, maybe it becomes like a mixture?
okay, so what we have some terms for that. What is the mechanism by which we could take like soil and sediment and move it with water?
Oh,
Floods?
Okay, floods, I agree, but what are the floods doing? What are they doing to pick up the sediment?
They're eroding it.
eroding.
Erosion. All right, so we can erode. All right, erosion of water or erosion and transport of sediment. What if I was thinking about my ways that I can get water to my stream? All right, so we had things like overland flow, we had soil flow, and we had groundwater flow. Which one of these you think, which one of those stream flow sources would cause erosion?
Overland flow.
Yeah. Okay, so really important. For phosphorus, we need overland flow and we need erosion. All right, because it's in the solid phase. When does overland flow occur?
Oh. When it's oversaturated, or
Okay.
it's or the precipitation is too fast for it to infiltrate.
Okay, so we can have so times of precipitation, right? That would be times when we have a lot of precipitation.
Yeah.
All right, so this would be during precipitation.
Um, could be what, snow melt or something like that.
So
Or
during
would you still consider that precipitation?
no, that's different. So snow melt. Sam mentioned one already where we get large areas of overland flow, and that would be flooding.
Yeah.
All right, so in fact, Carpenter talked about this. One of the big algal blooms that occurred in the Great Lakes was after a really large time of flooding. So they had a ton of flooding, they had a lot of erosion, and a lot of transport of sediment into the streams.
Mm.
Right? So in particular, they got a lot of phosphorus from that. All right. Okay, so overland flow, erosion, all right, it happens during precipitation, snowmelt, or flooding events. One thing that's important that I want us to think about is how rapidly these occur. All right, so this happens rapidly, all right, and it's of short duration. This, these time qualities are going to become important when we think about how long we would expect our system to take to respond. So if we have a big flooding event, we're going to expect some response, but also how rapidly, if we try to make an improvement, say we stop fertilizing with as much phosphorus, how long would that take for us to see an improvement in the water quality, right? And if it's really short duration events, if I change my behavior and I stop adding phosphorus to the soil, well, pretty soon I'm not going to be adding any phosphorus into my stream. The time scale of response is such that I very quickly can stop adding phosphorus to my stream. Okay, so phosphorus, generally sediment, has to be transported by
Yes, sir.
erosion. Yep.
You broke up for most of that, so would you go back over that?
Yeah, so the time scale, or how fast our system will respond, is important for two things. One is how quickly we expect it to respond to a disturbance like a flood, right?
Yep.
But the second is how fast we expect it to respond to something like a remediation or improvement in our practice. So let's say we decided to stop fertilizing with phosphorus. If I have something that it moves very fastly, then, or very rapidly, then I expect that if I change my practice, I will rapidly change the quality of the water. All right. So, for example, with erosion and transport, it happens fast. If I stop erosion or I stop fertilizing with phosphorus, then I will rapidly decrease the amount of phosphorus coming into my river or my lake. Okay, so phosphorus, largely driven by erosion. We can get some. So Mark talked about aeolian transport. So that's another way we can transport material. So wind blown. Or aeolian. All right, so dust and dust being blown, that's actually a fairly significant source of nutrients to some water bodies, especially the ocean. All right. And it can contain phosphorus in the dust particles. So we'll call this dust. So this is different than gas phase transport. It is still a mineral phase. It's just being blown by the wind now in the form of dust. And this one doesn't necessarily have to be during a precip event, but you do have to have the wind blowing. It happens rapidly, but dust blows more often than it precipitates, really. So there's sort of, it happens rapidly, but it's kind of continuous. pretty constant. Okay, so we've done solid, and solid is both nitrogen and phosphorus can get transported via these overland processes, all right? But for the most part, it's the only way we transport phosphorus. Okay, so we've covered, pretty much most of the way that phosphorus gets transported and most of the way that we're going to transport things in the atmosphere. There's one other way we can transport things in the atmosphere, and that is through air, through the gas phase. So nitrogen can go to N2, right? And this can be transported in gas phase. In fact, it's the majority of the atmosphere. All right, so we can get gas phase transport.
So would that count for all of your ions, like NO2, NO, those kind of things too?
All of those do have some vapor pressure, so you will have some nitrate, nitrite in the atmosphere, but that transport is pretty small in the gas phase. So the main transport of nitrogen in the gas phase is via N2.
N2, okay.
Okay, so now let's think about other ways that nitrogen can get transported in the subsurface, and phosphorus to a less extent. Both of these can get dissolved and put into the aqueous phase. All right, so let's think about some water that falls on our crop. All right, it goes through the soil zone and into our groundwater zone. All right, and it brings with it aqueous nitrogen and to a lesser extent phosphorus. So I'll put it in parentheses, phosphorus. All right. What are ways that we could transport this now aqueous nitrogen to our stream? What are types of flow that might transport this aqueous nitrogen to the stream?
All three.
All three of them would.
Yeah, so
Yeah.
all three, that's overland flow. We got interflow or soil flow. And then we have groundwater flow. Okay, so when we add these things to our hydrologic system, we can move them via soil flow and via groundwater flow. So one of the things that happens along the way, and one of the reasons why phosphorus doesn't get transported all that much, is that even if we dissolved it at the surface, we get a process that's called adsorption. All right. And this means things like phosphorus sticks to sediment or soil. All right. So adsorption is a pretty important process for transport. As we go, as if you go on and think more about transport processes, like, for example, we're doing research on a contaminant plume of uranium. So here, there was some uranium piled up on a riverbank, and the precipitation leached the uranium down into the groundwater system, and you're having the uranium flow along with the groundwater into the river. This process of adsorption is really important for controlling how fast that uranium will work through the system and move to the river. So this sticking of solutes to soils is a very important transport parameter. Okay, so nitrogen can get added, and it can come with both dissolved in overland flow and in soil flow and in groundwater flow. So let's talk about soil flow. All right, it still, for the most part, occurs during precip. Or let's say occurs close to the time of precip. Or snow melt. It has sort of an intermediate residence time. So let me say this. So here we're going to say by short duration, this guy has a residence time tau on the order of days. All right. Soil flow has a residence time on the order of weeks. All right, so we get a big precip event. We will have soil flow contributions to our river for the next couple weeks. All right. Well, what does that mean? That means that if I have a big precip event, I leach a bunch of nitrogen, I can expect an increase in nitrate in my stream for at least the next couple weeks from the soil flow. All right. So then the next one is groundwater flow. All right, and this occurs pretty much continuously. It has potentially quite long residence times. So here my residence times are on the order of years to centuries.
So wouldn't centuries be like your regional groundwater? And didn't we talk about that in 420, that that's usually not affected by um by uh, surface?
Um, well, uh, it's not going to respond rapidly. All right. So if
Okay.
you've got, so this is an important point about the groundwater component here, and one that is just now starting to get some attention. If I add nitrates into these big groundwater flow systems, it could
Mhm.
take 100 years for that nitrate to show up from groundwater transport in my stream. All right, it might take 100 years. The flip side of that is once it shows up, even if I make changes in my practice up here, that will take another 100 years for me to
That's-
see changes in water quality.
Mhm.
So this is a really important point. When we try to say do things to fight eutrophication, we have to think about how long each of these processes will take to affect our water quality. And one of the things that's been happening, so I'd say, over the last couple decades, there's been a lot of focus on trying to combat eutrophication. And a lot of education and outreach with farmers, changing of, in fact, changing our fertilizers to have a lot less phosphorus in it, um, changing practices so that we have less erosion. But we're still continuing to see quite a bit of eutrophication. And one of the reasons for that is that we've loaded the groundwater system up with nitrate, and we will continue to see that nitrate contamination for a long time. And so I have a friend of mine at University of Nebraska, and that's really his research focus, is thinking about how long will this nitrate contamination continue to occur for? And how could we try and predict sort of how long we can expect eutrophication um, from groundwater contamination by agriculture?
Is that like they have a huge dead zone in the Gulf of Mexico, and it occurs year after year. No matter what we try and do, it just keeps coming back because the nutrients have gotten into the deep groundwater.
Well, potentially. Let's think of other sources. It's a good example. What are other ways you think that we could get a lot of nutrients into the Gulf of Mexico?
I mean, we have the Mississippi.
Yeah, so estuaries in particular get hammered with nutrients because they have a large river that's draining to the ocean. So the Mississippi, goes through agricultural areas over its entire length. By the time it discharges to the ocean, it's carrying a lot of nutrients. And those nutrients get transported into the Gulf of Mexico. Another really important source of nutrients in the ocean is windblown dust.
Peyton, I have a question.
Yep.
Were there like dead zones in eutrophication before that happens before humans like started adding fertilizer and increasing the amount of phosphorus?
Yeah, absolutely. There's always been, so even natural wetlands actually can get very large dead zones. And even before we started changing the biogeochemical cycles in a big way, we had red tides and algal blooms. So it's not necessarily a new phenomenon. And we used to get them a lot from things like this: flooding or windblown events. If you added a bunch of dust, you had a big dust event, you added a bunch of dust to the ocean, you can get a big algal bloom afterwards, and then you get a dead zone. So they definitely happen regardless of our interaction. We've just we're mining a bunch of phosphorus and we're producing a bunch of bioreactive nitrogen from our better living through chemistry.
Yeah.
So we've just added to the problem, but it was always a thing.
I remember something from evolution and cows. They would, if they're kept pinned up, they would stomp on the ground and cause it to turn into dust, and that dust would get picked up by the wind and could be transported. And so we're talking like manure and things like that the cows eat, or food that they didn't eat, could be pounded into dust and then picked up and carried.
Yeah, so one of the interesting things here is that you're talking about is this system and all the potential feedbacks that we have. So as an example, you could have overgrazing, all right? And you reduce the crops, all right? Or the vegetation holding soil in place, and you get more aeolian transport. No problem. Or by reducing the vegetation, you increase the erosion. So an example of this is something that we see a lot is after a fire. So you got a mountain. Here's our stream. We had nice green trees and lots of veg, and then a fire rips through, and all we're left with is, our black stumps, and our veg gets used up. Our soil got burnt. All right. And then we get our first rainstorm. All right. So what happens the first rainstorm after a fire scar? You guys know?
Does it carry all the burnt sediment and like the dirt that isn't held down by the roots, or the soil's that's not held down by the roots gets traveled, so there could be a debris flow?
Yeah. So we get in general, so we'll say this, we got a fire scar. So we lost all of our veg that was holding the soil down. All right. And this funny thing happens, especially with the first rain, the soil actually becomes hydrophobic. It won't soak up water. So we get a bunch of increased overland flow. So we get a debris flow. We always do.
Do we know why it becomes hydrophobic?
Yeah, it changes the heat changes the chemistry.
Okay.
of the organic material in the organic layer of the soil. And basically, it changes it such that you make that soil for a while really act more like a hydrocarbon, and so that those hate water, so water won't go through the pores. Um, we usually wash that layer off in the first debris flow or two, so this is kind of a transient effect, but we do get this. We get a debris flow, we get a lot more erosion on our fire scar. All right, so what happens when we have increased overland flow? We increase erosion. And we get, generally in forested systems, phosphorus isn't quite the problem, but we get a huge nitrate pulse. But I'll put phosphorus in there too. Nitrogen and phosphorus pulse. So what we often see after fires is we'll get big fish kills after the first rain because we just dumped all this nutrient into the river, and we get eutrophication. So this is one of these feedbacks that, we had a drought, then we had a fire, then we get another rain, and then it will lead to naturally occurring eutrophication. So one of the so the important thing, or the main points I want you guys to take home from this exercise are, first of all, the three sort of phases of transport. So we can move it in the solid phase, in the atmosphere, or in the water. All right. And that each one of these brings sort of a different set of nutrients, say nitrogen and phosphorus if we're eroding and actually physically moving sediment, nitrogen and nitrate if we're dissolved, and that they have different time scales of response. So, overland flow and aeolian flow, they happen rapidly. But if you get nitrate in your groundwater, then you've got a very long-term sort of chronic problem. So these are more acute problems, and groundwater would be considered more of a chronic problem. And that you can really think about the feedbacks here between the ecosystem, weather, and the hydrologic system, and think about how you can, affect these biogeochemical cycles. So if we affect the ecosystem here, we change the availability of nitrogen and phosphorus and the ways that it can be moved to our water body. All right, so this is pretty much the end of biogeochemistry. I hope it's given you guys enough to appreciate sort of the complex interactions that occur and how tightly coupled the ecology and the hydrology and the biogeochemistry are. And that you can get these really cool interactions that really have huge effects on every aspect of the critical zone. So starting next week, Andrew's gonna start lecturing with you guys. am not sure whether he's going to do live lectures like me or just record them. I think his plan is to do live lectures and record them like I'm doing, but I'm not exactly sure. So expect some communications with Andrew over the weekend, let you know sort of how class is going to go. Do you guys have any questions for me right now?
No.
All right. Well, if that's the case, have a good Friday. Enjoy your weekend, and we'll see you guys in a while.
Thank you. Bye.
Cheers.